So activity 3.2 begins with a problem that involves cell phones. We're provided with a table here that lists the number of cell phones in millions for the corresponding years 1996 to 2000. Right, so you can see in 1996 there were approximately 44.248 million cell phones, or 44,248,000 cell phones. And right away we're asked, is this a linear function? How do you know? So you have to remember the test for linear function is the average rate of change. Are they consistent, right? Do we get the same slope? So we're going to have to show a test down here. So after I perform my average rate of change constant calculations, you'll notice I get an average rate of change of 11.064 million cell phones per year and 17.285 million cell phones per year. Right? I just took two ordered pairs and I calculated the average rate of change. And since the average rates of change are not constant, we can say this is not a linear function because the average rate of change is not constant. Next, we're asked to evaluate the indicated ratios to complete the following table. So ratio just means division. So when you look at 1997, the number of phones in 97 and the number of phones in 96, if we divide these two numbers, that gives us a ratio. So after I complete the successive ratios, I notice that I get 1.25 as my answer each time. So question B says, what do you notice about the values of the table? My answer would be the values are the same, or the values remain constant. So this constant ratio, it means something, right? And the book gives us a little definition. It says, we have an exponential function with a base of b, where equally spaced input values yield an output value whose successive ratios are constant. So in this case, right, our ratios are constant, our inputs increase by 1, and when you look at our table, the input goes up by 1, 96, 97, 98, and so on. So when we divide and get that ratio, the value that we get is actually considered our b. Now, if this b is greater than 1, we have a growth factor. If b is between 0 and 1, we have a decay factor. So when I look at our box here, our value for b is the 1.25. So since that's greater than 1, we have a growth factor. I look at question 3, and it says, does the relationship in the table represent an exponential function? The answer is yes, because successive ratios are constant. What is the growth factor? Well, that's that value b, right? That is the ratio. So in this case, the value for b is 1.25, and that is our growth factor. So let's scroll down to question number 4. Question 4 asks us to use the information from the table to write an equation in the form of n of t equals ab to the t, where n of t represents the number of cell phones and t represents the time. So before I do that, I just want to refresh our memory as to what the equation of a linear function looks like and what the equation of an exponential function looks like. So you know, for linear functions, we have y equals mx plus b. Exponential functions, we have y equals ab raised to the x. So we've already discussed that our b in this problem was 1.25. And the 1.25 came from our successive ratios, right? We did all of these division calculations and obtained the 1.25. So the successive ratios gives us our b. And the a would represent the initial value, or our beginning value. So if I were to use the letters y and x instead of n and t initially, my equation would look something like this. So I would have y equals 44.248, that's millions of cell phones, times 1.25 raised to the x. Right? Our b is the 1.25, our a is the 44.248. The 44.248 comes from our initial values of cell phones, which we get from our table, right? What's the starting value of cell phones? That was the 44.248, I guess, millions of cell phones. So now if we actually answer the question using the letters they've given us, the n and the t, our equation would simply be this n of t equals 44.248 times 1.25 raised to the t. Right? We've just replaced the y with n of t, and we replaced the x with t. Okay, and so this should give us the number of cell phones for any given t, or for any given year. And I just made a note on the side here, right? The 44.248 represents the initial value of phones, or the initial number of phones, and the 1.25 represents the growth factor. I actually changed value to number. I think this looks better. Initial number of phones. We're then asked, what's the practical domain of the function n? So for practical domain, right, see the practical domain, I'm going to go back to our table, and it looks like we go from 1996 to 2000. But you could also think of this 1996 as your base year, 0, 1, 2, 3, 4, right? We have 4 years worth of data. So I wrote my answer as the practical domain is between, t is somewhere between 0 and 4, right? Remember, the domain, we're talking about what happens to the input. What are the practical values for the input? And if I look at the table, my input goes from 1996 to 2000, but think of 1996 as my base year, or 0. So I'm going to use 0, 1, 2, 3, 4, because when I actually use my equation, this 44.248 times 1.25 raised to the t, I'm going to enter values 0, 1, 2, 3, 4. I'm not going to put in 1996 for t. I'm not going to put in 1997 for t. Right? I'm going to use the 0, the 1, the 2, the 3, and the 4. Okay. Next, we're asked to graph the function on our calculator, and then we're told to sketch the result in this box below. So let's pull out our TI graphing calculators. So I press y equals. Again, I make sure my plot 1, plot 2 are not highlighted. So if you were doing regression before, you want to make sure that none of these boxes are highlighted. So my equation is this 44.248 times 1.25 raised to the t. So I'm going to type it just the way I see it, 44.248 times 1.25. The exponent, use the caret key, and then press X. Now, depending upon the calculator you have, some of your calculators will actually write the exponent x as an exponent, and some will actually show you this caret symbol down here, and then the x. Both will be fine, and both will work fine. Okay. Now, we said our domain is going to be 0 to 4, so we're going to have to set up our window. So press the window key. And the window often gives students trouble. So my suggestion would be, let's go back to the table to get some clues for an appropriate window. So you notice my table goes from 0 to 4. So that's the input. So my x values, I'm going to say will go from 0 to, so instead of 4, maybe I'll go a little further. I'll go 0 to 10. Okay. And then my y values go from 44 to 108. So maybe I will start at 0, just to get a really good look at the graph, and I'll go past 108. Maybe I'll go to, I don't know, 175. Okay, so that's going to be my window. For scale, all right, well, if I count by ones from 0 to 10, that will give me 10 tick marks. If I count by, for the y scale, if I count by, really, if I just move the decimal one place to the left, if I count by 17.5, that will give me 10 tick marks on the y-axis. So I press the graph key. And there's my graph. And again, notice the tick marks here, right? I'm counting by 1, so this would be 1, 2, 3, 4, 5, and I'm counting by 17.5 on the y-axis. So you're asked to sketch that on your paper. So if you want to pause, maybe you'll fill in the graph here. And I'm going to ask you to forgive my sloppy-looking graph here. I did put the labels. But I'm trying to draw this curve with the mouse, and as you can see, I'm having difficulties. But again, doesn't have to be a Picasso, right? Just give me a basic sketch here, and I'll be happy. Part D says determine the vertical intercept of the graph by substituting 0 for the input. What is the practical meaning of the vertical intercept? So here's our equation, and I'm going to replace t with the 0. So when I place the 0 in, well, remember, anything raised to the 0 is 1. So I'm left with 44.248 million cell phones. So the practical meaning would be the initial number of cell phones in 1996, or our starting value for cell phones is 44.248 in millions. And then we're given another definition of exponential functions, right? It could be f of t equals a times b to the t. When t is 0, the b is the, where a is the value of f when t equals 0, and b is the growth or decay factor. And I think I've explained this equation back over here, right? The a is your initial value, the b is your growth factor.